Okay, picking up where we left off on page 384, we're talking about some new terms and concepts here. Talk about data warehousing and data mining. And these are things you kind of sort of need to know. So, data warehouse essentially is perhaps another database. It could be that you have a database that you use on a daily basis, and it has tons and tons and tons and tons of detail and goes on forever. But at the end of the year, for example, you purge the old data and start over. That's a very consistent way databases work. But somebody else in your company wants to look at old data from 2-3 years ago. So you have a separate data warehouse. And perhaps it's not the exact same data, and perhaps it doesn't have all the details, but because otherwise it would just be monstrously huge. And so there could be some upper level summary detail that gets stored in a data warehouse. So a data warehouse is typically a separate database that has summarized data and goes back way back. And the idea of data warehousing is these, like in the show here, about when you're doing data mining, you usually do data mining on this summary data, not on like a live production database, although you certainly could. And you can ask all sorts of questions of a data warehouse that would not make much sense in a production environment. For example, you could say, show me all the stuff that happened in the state of California, or show me everything that Bob did for last year. Or show me everything where these customer Sam, all these kinds of things where you're not asking for details, you're asking for big picture kind of things. And so again, other types of systems feed into this data warehouse, and historical data is rarely destroyed, and the details are significantly less. Does that sound like one of those which of the following are true of data warehousing questions? Yeah. Okay. So data mining, the purpose for data mining is to hunt for useful patterns. You can turn it loose, so to speak. There are applications out there that you give it data and you say, I'm interested in, let's say you're producing something, and you have some data that's collected, that collects manufacturing defects. And so you think, just go out there and look at manufacturing defects and see if you can find a pattern. So you're not really telling it, go look at this, go look at the Chicago plant, or go look at the evening shift, or you're not directing it to look. You're telling this piece of software, here's what I'm interested in. I want you to go out and detect a pattern for me without me having to tell you what that pattern is. And it could come back and say, whoa, the Atlanta plant produces 5 times the number of defects as the Chicago plant. Something might be wrong. And so you ask it, you can zero in a little bit more and say, do you see any patterns in the Atlanta plant? And then it says, the night shift produces 50% of the errors. You go, oh, cool. So you zero it again. It says, find me a pattern on the night shift in the Atlanta plant. And then it comes back and says, when Bob's on duty, there's an awful lot of errors. And so you didn't ask it, find me the employee that's causing the problem. You didn't ask it that. You just turned it loose and it said, we detect a pattern. You go, ooh, okay. And then you detected another pattern and another pattern and another pattern. And you finally discovered that Bob on the night shift at the Atlanta plant is your number one cause for these manufacturing defects. So that's what data mining does for you. It provides you all sorts of, now I will tell you, sometimes when you turn it loose, you end up with weird stuff. For example, we had a database that contained archaeological sites, as an example. And what they would do, they would go out on the field, particularly on the weekends, and collect data. And one of the patterns that it determined was that site records were updated on Mondays. And I went, okay. So it detected an unusual pattern in the day of the week that these things occurred. Now that was absolutely useless to me, and so I just kind of skipped that one and say, thank you, I don't need that, but continue looking for other patterns. So I'm not saying that every single time you turn it loose and let it run amok, that's going to provide you useful information like Bob in Atlanta on the night shift. That doesn't always happen. Okay. Let's talk about on page 387 the logical versus the physical structure. I'm going to go into slightly more detail than they do. And let's talk about this concept of, let's say, for example, that I want to do a query on a particular salesman. And he's been working with us for 3 years. What happens is, I just run a query and it produces me 3 years worth of data. And everything works. Everything's fine. But behind the scenes, I actually have broken my sales data into 2 tables. The current year's table, because that's the one that I'm almost always working with. And then I have another table behind the scenes, which has the historical data in it. Now, I didn't have to know that. I didn't have to know that to me, I have one table with sales data in it. And so when I write a query, I just give it the name of the table. And everything works like fine. But physically, behind the scenes, it's not called that. And physically behind the scenes, it's not one table. Physically behind the scenes, the relevant current data is on machine A, on table A. The historical data is on some other server. It has a completely different name. So the physical layout of the tables does not have to match the logical layout of the tables when I'm writing a query. I just say, select, all from customers where customer ID equals Bob, and everything works. I'm happy. So the difference between logical and physical is the way it's expressed to the users versus how it's laid out. Because how it's laid out, you could have that data replicated among different servers. The sales data could be on one server and the customer data could be on another server, and you should not ever have to know that. That's the whole point. Logical versus physical. Okay, on page 388, it talks somewhat from a historical concept of how you encode data. They had EBCDIC and they had ASCII and binary. Practically everything in a database now is done with Unicode. Unicode allows for so-called wide characters. Now, it used to be that, between 6 letters in the alphabet plus all the symbols and all the rest of that stuff, you could fit the entire keyboard of a modern computer in about 127 combinations, which just so happens to exactly match what fits into 1 byte of information. So that was pretty cool. And then they had a byte can actually store twice that many. So they had all the keyboard characters plus a whole bunch of other things you could throw in. I mean, you had all sorts of weird things, symbols and, mathematical symbols and stuff. And that worked pretty good until we started globalization. And then you go to France and they want diacritical marks and they want all these other symbols. Or you go to Russian and you have Cyrillic alphabet and you go, whoa, I'm running out of room. When he went to the Asian countries, they went, to China and Japan, where they have, kanji characters and stuff. Then there's no way in heck that's going to fit in a full size of a byte, 256 combinations. So they had no choice but to expand the choices, so to speak. So now a single character in a database is actually 2 bytes wide, and that's generally sufficient to handle all languages. Okay, so you'll rarely find ASCII in a database, a modern database now. They just, by default, when you fire up a database, you say, I want to create a table, and everyone practically tells it I want, a wide character to store character data. That doesn't have any real context with numbers because pretty much all numbers are the same all over the world. Okay. The next one, though, on page 389, they talk about storing dates. And I told you a story about, the Y2K problem. All the world's going to come to an end, because the databases only have 2 digits for the year. And quite frankly, for quite some time, database companies have been producing standard ways of producing dates. The current SQL standard is called SQL 2011, and they very specifically talk about date formats. So there's an ISO standard specifically for dates on how you should store that. And there's different levels. You can have a very, very precise date time, go down to milliseconds, or you can have a generic kind of a short date file format, which isn't quite so strong. But anyway, bottom line is, if you're using a relational database, you're probably already using a standards-based date without you even knowing about it. Now, contrast that to a file-based system, like coming out of a GPS or some other piece of equipment. You're getting whatever the heck the manufacturer did. That's it. Okay, on page 389, they talk about the controls that can happen in a database, because I don't want a database out there that everyone can mess with, so I have to have some controls. So they talk about a well-designed DBMS must provide built-in control and security, including subschemas, password, encryption, audit trails, backup, recovery. All those kinds of things are an integral part of a relational database. Typically, when you buy a relational database system, it comes with all of that. You don't have to go buy a backup and restore application. It all comes with it. You don't have to buy an encryption routine. It comes with it. You don't have to buy some sort of a way of storing passwords. No, it comes with it. Okay, thankfully, we're at the end of the chapter on page 391. Let me just go through the chapter summary, and we'll be done. Okay. Database consists of linked tables that form an overall data structure. That's cool. Database management system is a collection of tools, features, interfaces that enables users to add, update, manage, access, and analyze data. Cool. A DBMS design are more powerful and flexible than file-based stuff. Yep. DBMS components include the user, database administrator, and related systems, a data manipulation language, a schema, and a physical data repository. An information schema, in an information schema, an entity is a person, place, or thing for which data is collected and maintained. And the primary key is a field or a combination of fields that uniquely and minimally identifies a specific record. That's a pretty doggone good definition. A candidate key, I don't care about that. Okay. An entity relationship diagram, an ERD, is a graphical representation of all the entities and their relationship. Oh, gee, why is it called an entity relationship diagram? Relationship between two entities also is called cardinality. Normalization is a process of avoiding problems in a data design. That's actually a pretty good definition. The purpose for normalization is to prevent problems. I like that. Data design tasks, including creating an ERD, completing the data dictionaries, and finally building your database. They talk about codes. Codes are a set of numbers, letters, symbols that represent data. The logical storage is the information seen through the user's eyes. I think I have a single customer table, but in reality, it could be multiple. It could be multiple servers. So how it's actually organized, not relevant. Physical storage is, the hardware, related to how things are put together. And then file and database controls include limiting access, that's obviously pretty cool, data encryption, backup and recovery, audit trails, and all those kinds of things. So, we've reached the end of the chapter, and we'll see you again in just a few for Chapter 10.